That drawing is legal student working with applies, and you will be talking about his thesis work, basically. So Krylov complexity of chiral quantum walks.
Okay. Hello, everyone. So, Professor already did the introduction, so I'll start with the content. So, first of all, let's define what are the two main words in this presentation. So, chiral quantum walks and Krylov complexity. Let's start with the former. What is a quantum walk? A quantum walk is basically just the ordinary Schrödinger equation packaged in a different way. So let's start with a Hilbert space for which we choose a basis, and for which we have a unitary operator, the Hamiltonian, generating the dynamics. Then this couple, basis and operator, can be mapped to a graph following these rules. The states, the orthonormal states of the basis, are the nodes or the vertices of the graph, and we connect two elements of the graph, two vertices, with an edge, if and only if the matrix element of H in these two states is different from 0, and also we assign to it a weight equal to the matrix element itself. So then we can choose any initial state, which will be expressed as a superposition of the elements of the basis. So in general, a superposition of the vertices, and turn on the dynamics generated by H. And this process is called continuous time quantum walk, with respect to discrete time defined in a bit different way. So as you can see, it's just a Schrödinger equation, unitary evolution. We're just describing it in a different way. Usually, for practical applications, what's done is that we do the opposite. We have a structure which can be described by a graph, and then study the dynamics defined on the graph. I prefer this approach because once the Hamiltonian and the basis are given, the graph structure is uniquely defined, while for the same graph topology, many different Hamiltonians can be defined. So, as widely studied in literature are because of this of the second way of describing quantum walks, which is from graphs to Hamiltonians, is restricted to real Hamiltonians. So Hamiltonians whose entries are real elements and real numbers. And so, because H must be a Hermitian operator, it being real implies that it is also a symmetric matrix. This symmetry constrains the dynamics in more ways than necessary. For example, if we study only the transition probabilities between two different nodes, so two different elements of the basis, these probabilities are time reversal invariant. So we can see that the probability of going from I to j in time t is equal to the probability of going from I to j in time minus t, which together with the general symmetry given by unitarity, which is that in general p of I to j is equal to p of j to I in minus t. Together with this, we can say that the probability of going from I to j is the same as going from j to I for any time t. And this is a constraint to the dynamics because, for example, for topologies which have a reflection symmetry. For example, imagine a closed chain. Then the probability, if we start the walker in one of the vertices, the probability of going to a vertex and to its symmetrical one is the same. And in particular, these probabilities cannot be larger than 1/2. And this type of Hamiltonians are called non-chiral, because in this kind of graphs, there is no directionality. It's like as if the system does not distinguish between left and right. That's the reason for the word chiral here. So one could be interested, this is a limit in, for example, transport problems, because you can never exceed the 1/2 bound for the probabilities, and so it's difficult to transport, for example, in a molecule, an excitation from a specific node to another one, or to route information. So the necessary generalization to do to break the symmetry is add complex phases. So now we explore the full power of Hamiltonians, which are Hermitian operators, not symmetric operators. And to do so, we must have that the matrix elements are complex numbers, so with a complex phase. And opposite to the other ones, these ones are said chiral, because, for example, now in a chain, we have the possibility to distinguish between left and right, because the probability, because of course, since H is Hermitian, if the phase between J and K is phi, the phase between to go from K to J is minus phi. So this affects the probabilities. It has been studied in literature already, this possibility. And for specific topologies, it can happen that the introduction of phases allows us to achieve better transport. For example, in the quantum switch, which we will see later. But there's a caveat to this, because in general, adding phases is necessary, but not sufficient to have different transport probabilities. This is due to this symmetry, this class of symmetries called quasi-gauge equivalence, quasi-gauge symmetries, defined similarly to what gauge symmetries in high energy physics are. So it's just a local rotation by a complex phases of the elements of the basis. And this might seem harmless, but it's not, because we can prove that even though H is not necessarily invariant under such a transformation, the transport probabilities are. So if we have two Hamiltonians which are related by a quasi-gauge transformation, the probability of transport generated by the two Hamiltonians of going from and to localized states does not change. This means that even though we add some complex phases, but the Hamiltonian we end up with is still related to a real one, then we will have achieved nothing. The probability transports are still equal to the ones of the real symmetric Hamiltonian. One way to study quantum walks is given by Krylov methods, which are a way to reduce the dimension of the Hilbert space where the dynamics unfolds, so that it's easier to tackle the problem. Let's see it more in detail. it starts with this almost trivial observation, which is that the time-evolved state is defined as an infinite series of different states, which are the image of the initial state through the nth power of the Hamiltonian. But if the dimension of the Hilbert space is finite, then of course these different states will eventually be linearly dependent. So we are basically saying that we are considering more terms in this series than necessary. We can resum it in a more clever way. So it happens for K, which might even be less than the dimension of the Hilbert space. Consider this trivial case. If psi 0 is an eigenstate of the Hamiltonian, then there's only one linearly dependent term in this sum, which is psi 0. All the other ones are just psi 0 multiplied by powers of the eigenvalue. So we have just a sum of numbers, a series of numbers, and psi 0 itself. So we define this subspace called the Krylov subspace. This is the span of all these powers up to k, which implies that h to the k applied to psi 0 is linearly dependent to all these other ones. And small k is the dimension of the Hilbert space, of the Krylov subspace. And one, from this simple, from this naive hand-wavy argument, it can be rigorously proved that K is the minimal subspace containing the dynamics. Thinking again to an eigenstate, in that case, the Krylov subspace would have dimension 1, because it would just be the span of psi 0. So, with this choice of basis, by the way, those terms are not the bases themselves, because they are in general not orthonormal. They have to be orthonormalized, which can be done with some computational methods, for example, Gram-Schmidt algorithm. And whenever it happens that K might even be orders of magnitude less than D. So the dimension of the Hilbert space, of the Krylov subspace, might be orders of magnitude less than the dimension of the Krylov space, of the Hilbert space. So it was introduced and widely used in condensed matter and quantum chaos, and in general systems when, since we have many particles, the dimension of the Hilbert space scales exponentially. But also quantum walks benefit from this technique. And the main example is a complete graph. A complete graph with n nodes, a complete unweighted graph. So each edge, imagine that each edge has only value 1, or at least they all have the same real value. And for this type of graph, of course, the dimension of the Hilbert space is n, but it can be shown that any dynamics given any initial state can always be reduced to the one of a two-level system. So it doesn't matter how large n is, we will always require no more than two states to describe the system. This is important, for example, in one of the applications, which is the Grover's algorithm. So the Krylov basis also has this property. Here Kn are the Krylov vectors, which are the orthonormalized version of Hn applied to psi 0, which is that H is tridiagonal in this basis. So not only we have a smaller subspace, but we also have a simpler expression for the Hamiltonian, which acts almost as the combination of number operators and increase and ladder operators. This means that in terms of graphs, we can always start with a generic graph, and we can map it to a chain where each element, each node is an element of the Krylov basis. And this means...
Is this true for any age, or what's the structure?
It's true for any age. It's just the definition of KNs made to satisfy this relation. Because if you think, H is like, if we unwrap what's in Kn, is H to the n applied to psi 0 minus other stuff, which makes it orthonormal to all the other ones. And we are applying H again. So we will have a term which depends on Hn plus 1 applied to psi 0, and other terms which in general are just given by this combination.
It's like it gives you a useful effective description, assuming its state, right?
Yeah, I should have stressed more about this. Yes, it's given an initial state. So you are given the pair Hamiltonian and initial state, and you define the Krylov subspace uniquely, and the Krylov basis uniquely. Clearly, of course, yes. Yes. Which is but once the starting point is fixed, all the other elements of the chain are fixed as well, given, of course, the evolution operator.
And so K0 is just psi 0?
Yes, it is. It's since we assume we start with a normalized state, psi 0 is the starting point, and yes, it's K0. So that's why it's useful in quantum walks. And now, after this introduction, we can introduce the main quantity, which is the motivation of my thesis, which is Krylov spread complexity. So we have constructed the Krylov subspace. We have the Hamiltonian expressed in a three-diagonal form, and we can define this quantity. This quantity is basically, we are evaluating the expected value of the number operator. So we are saying that this is the average position of the walker on the chain at a time t. And here we have a pictorial representation. This was initially done for operators because, of course, operators themselves are part of a Hilbert space, so they can be seen as vectors in a Hilbert space with the product given by the Hilbert-Schmidt product. So, but the reasoning is the same. You have phi n, which is this overlap, and you have the walker hopping on the chain. And at each time, you can basically describe all the moments of this distribution on the chain. And this is the first moment of it. This is the complexity, which tells you rather how, it doesn't tell you how spread the walker is on the chain. It just tells you how far it goes on average. And since it was introduced for operators, only recently it was studied on quantum walks. It was studied very extensively in this work in 2022. And here basically complexity for many different topologies were computed, showing, for example, that on the complete graph, complexity decreases as the size of the complete graph is increased. Always an initially localized state is assumed. That's an important caveat. And the question is, the problem is that this work was, of course, it was a seminal work, so it started simple. It started from real and symmetric Hamiltonians. In particular, Hamiltonians that evaluate each edge with 1. So those are called adjacency matrices, and only this kind of Hamiltonians, which are affected by all the limits we were discussing before, were studied. So the question motivating my thesis is what happens to complexity when complex when phases are considered. So when complex Hamiltonians are brought into the game. So we start with my results, what I've achieved in this work. First of all, since making computations makes you reason a lot about the tools you're using, I was able to find some non-trivial relations which are not directly connected to the application of Krylov complexity to quantum walks, but rather concern Krylov complexity by itself. And I give this definition because it becomes useful for the time being to restrict ourselves to a specific basis of eigenstates of the Hamiltonian, because in literature, many times only non-degenerate Hamiltonians are considered, but actually the degeneracy of the Hamiltonian is what makes the Krylov reduction method work. So it's useful to talk about it. And so I always assume we are in a basis of the eigenstates for which the spectral decomposition of the initial state is non-degenerate. So in all degenerate eigenspaces, we always rotate the basis such that only one element aligns with psi 0, with psi. So given this definition, we can state some propositions. First of all, it is not given in general to know when to stop, when to, it's not simple, or at least it was not given, what's the dimension of the Krylov subspace given an initial state. And what I found is a criterion that tells you that the dimension of the Krylov subspace is equal to the number of degenerate eigenspaces that in which psi 0 can be embedded, eigenspaces of the Hamiltonian, which in turn turns out to be the cardinality of the minimal basis. Because all the, of course, if we have two different eigenstates that appear in the spectral decomposition of psi, we can just take their linear combination and define it again as an element of the basis of eigenstates, which is doable because, of course, any combination of two eigenstates with same eigenvalue is still an eigenstate. So, and these ones will count as a single state in the dynamics because they evolve with the same phase. So this is the first proposition, and this brings a corollary, which is that we cannot have, given any initial state, we cannot have a Krylov subspace which is bigger than the number of degenerate eigenspaces of H. And this justifies the claim about complete graphs, because a complete graph has this very simple spectrum. One eigenvalue with degeneracy 1, and all other n-1 eigenvalues are equal. So it's only two degenerate eigenspaces. We only have two independent eigenvalues. And therefore, given any initial state, it can be decomposed in this way, where E0 orthogonal is just a choice in the orthogonal subspace of E0. In particular, the choice that appears in psi. So, of course, the Krylov subspace and therefore the dynamics unfolds in a two-dimensional Hilbert space. So the Krylov subspace has dimension 2. This is somewhat trivial if you think about it, but it was never stated, so it was never put blank on, like, it was never stated so clearly. And another property I found, which I found it incidentally while trying to compute something else, is that there is a relation between, it's easy, this one is the, this complexity with the bar is just the time averaged from 0 to infinity of C of t. And it can be proved that if we have an initial state which on its minimal basis is equally spread, then it's easy to compute C bar without even computing the Krylov basis, and it just yields this value. And then we have another rather interesting, at least to me, result, is that not all values of complexity, or not all values of complexity are independent, because if we have a unitary operator which is which commutes with the Hamiltonian, then two initial states that are any two initial states that are related by such unitary transformation will always have the same complexity, because what we are saying is that up to a change of basis, the two dynamics are equivalent, because this is a symmetry of the Hamiltonian. This is particularly interesting for continuous symmetries, because it means that we have entire, like, sets of states, entire orbits of these unitary transformations, these unitary groups of transformations that all have the same complexity. And the last theorem I found, which it might seem similar, it might seem the same as the previous one, but it's actually quite different, is that we have quasi-gauge invariance of spread complexity, which is remembering what a quasi-gauge transformation was, which was a local rotation by a phase of the basis of nodes in a graph. So this is more strictly related to quantum walks. Then if the initial state is localized, so it's one of the nodes, then the complexity of two dynamics generated by Hamiltonians which are related by a quasi-gauge transformation are always equal. This is not, let's see how this is not a consequence of the previous theorem. It's easy, because in general, we are not asking lambda to commute with H. H prime and H are two different Hamiltonians. If lambda and H commuted, they would be the same. But here, the two transformations, the two operators do not commute. So in general, lambda is not a symmetry of the Hamiltonian. That's why we have to restrict to localized states. Otherwise, if it was a symmetry, it would be true for any initial state, while it's true only for localized states. And this is also not a consequence of the invariance of probabilities, of transition probabilities between localized states, because if we take back the definition of complexity, which is quite back here, this Kn, even if psi of t is psi 0 is localized, these Kn in general are not. The Krylov basis, the other Krylov vectors of an initially localized state are in general almost never localized. So this is not a trivial consequence of this. It's a consequence given by the structure of the Krylov basis and how it is defined. So now we go to the zoology part of my thesis, which is studying many different topologies and see just what happens when we introduce phases. Here, for example, we have this topology, a chain, a closed chain. And because of quasi-gauge invariance, we only have one independent phase, which is phi. So we consider an Hamiltonian for which any edge has the same phase. This is called a circulant Hamiltonian because it has Zn symmetry. So we see that this one gives the results for real graphs. It zigzags like this because there's a slight difference whenever the chain length is even or odd. But up to this, we see that complexity is not very high. I mean, they both grow linearly. This does not change, but is much less than in the phase scenario. We see the reason for this because of in the Krylov dimension. This is the dimension of the Krylov basis, which is bounded by symmetry in the real case, because we have time symmetry, and in particular we have a reversal symmetry of the graph, and this basically tells you that it gives degeneracy to the spectrum, and for the reasons given above, the Krylov subspace can never exceed like half of the dimension of the Hilbert space. And this constrains the dynamics, while the effect of phases is basically to break the degeneracy of the spectrum. And therefore, the worker is now free to explore all the Hilbert space, yielding therefore this clean linear result, which, by the way, is 1 over 1 is dimension minus 1 over 2, because in this case the initial state is equally spread on the basis of eigenstates, so it's a minimal IPR state, and therefore the theorem from above holds true. Similar behavior is seen when higher degrees of connectivity are added. Here we always are studying a circulant Hamiltonian, so all edges have the same weight, and this is the real case. The case with a phase is not shown because basically for aesthetically reasons, because otherwise all this behavior would be packed in the lower part of the graph, but we have that behind this thing. we always have this result, d minus 1 over 2, because again, the effect of the phase, now we have two independent phases. Again, the effect of the phase is to break all the degeneracies of the Hamiltonian. So the spectrum of the Hamiltonian becomes non-degenerate, so the basis of eigenstates is unique. And once again, we have that an initially localized state, 0 here is the initial state, is always maximally spread on the basis of eigenstates. And so we have this value of complexity, which I have the temptation to call the maximum value of complexity, but it actually is not. It's not necessarily the maximum complexity. It might look like it, but it's not. Then we move to more interesting topologies. If you remember, I talked about the quantum switch, which is this kind of topology, even with longer tails. And this one was one of the first topologies studied in the context of chiral quantum walks, because of course this one has a reflection. If the Hamiltonian is real, of course this graph has reflection symmetry. So the probability of going left to 2 and the probability of going right to 1, starting from 0, is the same. So you can never, if you want, for example, to direct some information from 0 to 1 or to 2, that's why it's called a router, you can never do it with more than 1/2 of probability. But this is different if you introduce a phase in this loop in the center, which gives you directionality. So now the system is able to discriminate between left and right, and so for certain times it will be easier to go to 1, and for other times it will be easier to go to 2. So in particular, values of theta equal to pi2 or 3/2 pi achieve a 633% of increase in fidelity, which is just enormous. So I studied numerically what the complexity tells us of this behavior, and the answer is not quite much. It just tells you that for values, for those optimal values, complexity is maximal, which we can interpret on the fact that the walker can explore more the subspace of the dynamics, which in this case, by the way, is the whole Hilbert space. Here the dots, the white dots, are to show that here there's a discontinuity, because these particular values of pi restore some degeneracy. Those are the ones for which the Hamiltonian is equivalent to a real one, so we have this symmetry and therefore degeneracy, for which complexity is much, much lower. But still, this is interesting because this is the first graph we see where there's a non-trivial dependence on the on the phase, because in the other cases, no, and I'm spoiling the results. In these cases, the actual value of the phase is not important. I should stress this, that in these cases, phi being 0.01 or 0.02, as long as the degeneracy is broken, the complexity is insensitive to these changes. Here, the case is different. So we have a non-trivial relation. So, yeah, sure. Yeah, actually, since the evolution is unitary, for certain times you will have most of the probability localized in 1, and periodically most of the probability in 2, and they oscillate. The fact is that introducing a phase maximizes this oscillation, while in the real case you have that for all times the probabilities are equal. Yes, and while in the, of course, you cannot, unless you go to open systems for which you put wells in these nodes, for which when the worker goes there, it captures it. But if the evolution is unitary, of course, it will always oscillate between 1 and 2. Was this your question, or yeah? Okay. And tangentially, this is not strictly related to introducing phases in the Hamiltonian. We wanted to know, as one of the questions is, but what is actually complexity telling us? What is it a figure of merit for? And one way to investigate this was to say, since complexity is dependent both on the Hamiltonian and the initial state, what happens if we average over the initial states? And I did for a quite simple graph, which is just a triangle, which is both a complete graph and a cycle graph. And I studied the distribution of complexity by given a uniformly distributed initial state. And this is the histogram. We see that the behavior of this histogram is not entirely clear. We see that for some reason maximal complexity states are preferred, but for a large region of these values of complexity, the distribution is quite flat. So if you wish, if we would ask, is it sensible to ask for the average complexity of a Hamiltonian? My gut feeling is that the answer is no. It's not very informative as a number, as a quantity. It's
on this
yeah, this is just the standard parameterization, and they are sampled uniformly on the. Sorry? What random states? Those are hard random states. Like they are. You mean they are sampled to the according to the Haar measure? They actually are. Yeah. They are defined on. This is particularly defined on the complex projective space of dimension 3, 2, 3. Yes, it's Q-trit.
Okay. Then the question is.
Okay.
What if it's not?
You will get a different distribution for sure, and I don't know, maybe a skewed distribution might maybe enclose. Maybe we could start. I guess we could start with this in a real life application, in a technological application. Usually the initial state is localized. But then maybe we are not so good at creating localized states, so we have a certain distribution around this localized state. I might see that as a motivation for trying different samplings. But again, I don't think that complexity by itself would be a very useful figure of merit for this kind of problem. Like this kind of, it wouldn't tell you much of the properties of the system or the Hamiltonian.
I mean, in this picture of the triangle, I
I don't know, maybe the some simpler picture is like a missing chain of I don't know, the units, but be a bigger graph, I guess.
Yes.
Much bigger. And I guess if you have R global versus R local states,
Probably. Gut feeling. I didn't investigate this type of systems, but I guess it would make a lot of difference because now every node has some internal degrees of freedom. That's what you're describing. You could as well describe it as a graph. It would have a different topology. You would have. It's difficult to say that without drawing it. Okay, but of course, it would map to a completely different graph, and it would have a completely different outcome for sure. And okay, and the last of my results was a bit of a fun exercise, which is as complexity tells us how far the worker goes in the Krylov chain. What if we use it as a measure for localization of eigenstates, which is we start with a localized state, and we expect that the more localized the eigenstates of the Hamiltonian are, the more this initial state will stay pointed where it is. And this is, for example, the case in this model, which is the Anderson model. It postulates a chain. It is a tight binding model. So it's just a chain with some hopping amplitude between sites and some on-site energies which are random. Uniformly sampled from this interval where W is called the disorder of the system. This, for example, is a simple model to describe how doping a conductor makes it become an insulator, because as eigenstates exponentially localize, then the transport of localized states, read electrons, becomes more difficult. And this is actually the case on the x-axis. We have complexity averaged over realizations of Hamiltonians, and we see that starting from a node, from a node of the chain, we see that here is the disorder W. Increasing the disorder makes the complexity fall. So what we are observing is that the complexity may be used as a figure of merit to see how much this Hamiltonian, this system, is able to oppose transport between the nodes. So it basically tells you here the chain is conductive, and adding some noise, so some, for example, impurities, makes it an insulator chain. And sorry? Oh, the curves. Yes. To provide them more robustly the result, I tried different initial states. So 0 is at the edge of the chain, and this is a 10 nodes chain. Technically, the Anderson model is an infinite chain, but of course I cannot put an infinite chain in Python. And we have an initial state which is on the edge. I'm just testing if this behavior changes if the initial state is in the center of the chain or at its edge. And we see that qualitatively at least, the behavior doesn't change. By the way, these error bars are magnified by a factor of 5 because they were too small to be visible. So the answer here is yes. We can use complexity as a measure for localization. Is it optimal? It should require further study. This is just a qualitative result. And this is it. Thank you for your attention.
Questions?
Yes? Yes. I always studied initially localized states, except for the purpose of generating that histogram. Yeah, yeah. Non-localized states. That's this example is it serves me because actually for states which are maximally spread on the basis of the eigenstates, not on the basis. You're thinking about the flat state, aren't you? Like on the. For the cases I've studied, this is not very interesting. This particular state is not very interesting because it's an eigenstate of the Hamiltonian. Circulant Hamiltonians have the flat state as an eigenstate, so it would just evaluate to 0. But yeah, why one might think about adding phases, like a flat state, but with some phases, which would not be an eigenstate, and in that case, I don't quite know what to expect. So, short answer, no, I didn't. But of course, this is a very scalable type of work, which can be made arbitrarily complex. But well, if I had to guess, I don't think they would go above this bound, because this bound is already given by a Krylov space which is maximal, which is all the Hilbert space, and it's given by states that are, well, I might be wrong, but my gut feeling is this. Did it answer your question? Okay.
Maybe one thing about this particular, you use the same place
for all the edges, yes.
But what if you add states, bases like 1 by 1?
Thank you for your question. I considered this, and for this topology, actually, it makes no difference because of this theorem, this one, because it can be proved that for a cyclic graph, any phase configuration is quasi-gauge equivalent to the configuration where all the phases are equally spread. The only caveat is that the sum of the phases must be the same. So actually, that's the reason why I got to prove this theorem, because I was trying to figure out what would happen. I was computing numerically the case for the arbitrary case with arbitrary phases, and I always got a flat graph. So the complexity didn't change, and that's what made me realize that in this case we have quasi-gauge equivalence that prevents us from changing. the value of the complexity, because you can always read your Hamiltonian as an Hamiltonian, a circulant Hamiltonian with phases equally spread. For honesty, this is not true in this case, because in this case, one can prove that the number of independent phases allowed by quasi-gauge symmetry is equal to the number of independent loops in the graph. So here, no, not here. Here we only have a loop, so one phase. Here we have a certain number of loops, because these are non-planar graphs, so maybe they are if I draw them here. Okay. Here the number of phases is higher, so actually it's no longer true that any phase configuration is equivalent to a circulant one. So in this case, this difference would show up.
One last.
It's right to see if complexity can also provoke some other fields like star states.
Sorry, which?
Star states. The neutralized spaces should break ergodicity.
Okay. Ergodicity. Yeah. I reasoned about the relation between complexity and ergodicity, but I think they are quite a bit orthogonal to each other, because
You can form even if they're related models.
I think that we can see some relation, because what I told when I defined the complexity is actually just the first moment of the distribution of this distribution. We can also define the second moment, which is we will call it the Krylov variance. And I think this one is more related to ergodicity, because it tells you how much spread the Walker is in the Krylov subspace. So if we restrict ergodicity to the Krylov subspace, I think that it would be more closely related to ergodicity if we consider the second moment of this distribution rather than the first one, because this one doesn't tell you exactly, it doesn't tell you how spread it is. It just tells you if it goes a lot far in the chain, or if it goes, or if it stays in the lower part of the chain.
Okay, let's talk about